Hello and welcome back to a video series on MAC 1105 College Algebra. My name is Sean Perry. These are guided notes number 26 in the series on section 5.4, exponential and logarithmic equations. Similarly to solving equations involving radicals with an even index, solving logarithmic equations will require us to check our answers. We may, in the course of solving these equations, produce what are called extraneous solutions. These will be solutions that will be outside of the domain of the logarithms in question. This will not be as much a problem with exponential equations, although it never hurts to check your work. Question number 1 asks, if 4 to the power of 9 times z minus 6 is 64, what's z? There's a couple nice ways of approaching this problem. The first is to use comparison of exponents. Once the bases have been made the same, and 64 is a power of 4, so we could write that as 4 to the third, we can just equate the two exponents, 9z minus 6 and 3. We're allowed to do this because exponential functions are one-to-one, or injective if you prefer. This means they pass the horizontal line test, and as such, when two injective functions are equal to each other, their arguments can be set equal to each other. Solving, once this has happened, is really just solving a linear equation. Bring that 6 over to the other side as a plus 6, and then divide by 9 to get z equals 1. Another way to proceed is to cancel the 4 to the power of part of this by doing its inverse operation, which we've seen is log base 4. Now, this is the same thing as writing it in exponential form. If I had left this 3 here written as log base 4 of 64 equal to 9z minus 6. But I've just evaluated that right quick. Log base 4 of 64 is 3, and then solving after this point is exactly the same as the other method, to get z equals 1. I think this first method is easiest when you can see that there's a common base on both sides. And this other method is a good method to use. We don't necessarily know that this over here was a power of 4. If I had just typed in log base 4 of 64 into the calculator, or log of 64 divided by log of 4, if I had a scientific calculator, I would have gotten 3 straight away. Furthermore, if 64 hadn't been a power of 4, and we'll see problems like that very soon, we would have needed to take the log base 4 of both sides, or at the very least taken some kind of logarithm in order to free things up and proceed. But we'll see that in due time. In the meantime, let's go on to the next problem. Here we have 100,000 to the power of x is equal to 1,000. What's x? Again, I think this is best done by writing both sides with a common base. And rather than thinking about what power of 1,000 I should be raising to get to 100,000, what we should do is write them both as base 10. 100,000 is 10 to the 5, and 1,000 is 10 to the 3. And so using the power to a power as a product of powers property here, we're going to wind up with 5x and 3 as the exponents. Setting those equal to each other, we can solve for 3/5. So if you want to get 100,000 to some power to be 1,000, raise it to the 3/5. Number 3 gives us another one where we might be able to tell that these are both powers of 2. 256 is 2 to the 8th power, and 1 over the square root of 2 is 2 to the negative 1/2 power. It's a negative because it's in the base, and it's a 1/2 because that's the index of this radical is a 2. Now setting these two exponents equal to each other, we can get z is equal to negative 1/16. Number 4 gives us one involving e. Here we need to see that 1 over e is just e to the minus 1 power, and so once we have a common base, we can set these exponents equal to each other and solve in the linear way. Minus 4 to give me negative 5, and divide by 2 to give me negative 5/2. Number 5 has a very similar vibe, but for tens, powers of 10. I need to see that 1 over 100 is 10 to the negative 2. Then once the bases are equal, we can set the exponents equal and solve the linear equation, adding 5 and dividing by 3 to get 1. Number 6 finally gives us a problem where one of the sides of the equality is not just some power of the other side, right? Here I have 10 to the w, and over here I have 1.94, which is no clear power of 10. What one should do at this point is to take the log base 10, which I've written here as the common log with no explicitly included base. That means it's base 10. So we take that common log base 10 of both sides. 10 to the power of is canceled by log base 10. And so we just get w here, and we've solved. On the other side, though, we have log of 1.94, which does not simplify. In fact, it's not going to be a rational number even. What we're going to need to do is evaluate this on the calculator. A calculator will give you 1.28780 and so on, and so we have this as approximately 0.2878. Remember, to evaluate these things on the calculator, we have two easy bases. We have log, which is log base 10, and ln, which is log base e. Log of 1.94 could be written this way, and this gives us our answer. Number 7 gives us a similar problem for a base of e, and it can be solved similarly quickly. If I take ln of both sides, it cancels e to the power of, and just gives me t equal to the following. If we wanted more decimal places, like if we wanted 4 significant figures rather than just 4 decimal places, we could go out a little bit farther using the calculator this way. As it is, I believe they ask for 4 decimal places, which would round to 0.0677. Be careful about the difference between rounding solutions to 4 decimal places and 4 significant figures. While there are some special rules that you need to know to really be fully cognizant of significant figures, basically when we're rounding these kinds of decimals, just make sure you don't count the leading zeros when you do so. We'll talk more about this significant figure question when we move on to the word problems in the next section. A note on exact versus approximate form. There is no more exact way to write the answer for these two problems besides the answer with the logarithms in place. That's why I've used equality for these first two answers. Every decimal that we can write down, every decimal that doesn't continue on forever, is going to be only an approximate answer, which I will try to indicate consistently with an approximation symbol. I will also try to consistently use a dot to indicate that this decimal continues forever if I'm going to use equality at some point after evaluating a logarithm, and this is mostly just to show you where I'm going to round in order to get my approximate answer. Question number 8 asks, 3 to the t is 69, what's t? The main idea here is that we need to take the log base 3 of both sides, or write things in logarithmic form to match this exponential form. If we do so, log base 3 of 69 will evaluate as such on the calculator. Let's see a couple ways to do that. Recall that if we have a sufficiently advanced TI-84 going to math and down to log base, we can actually put a base in, like 3, and take the log base 3 of 69 directly. On the other hand, if we have a less sophisticated calculator, we'll need to use the change of base formula. Picking either log base 10 or log base e, we can write this as log of the argument divided by log of the base, which you can see gives the same answer. One of these might be necessary if you're, say, for example, just using a basic scientific calculator. So this would be our exact answer, and this our approximate answer to 4 decimal places. Number 9 is similar, except now we have a little bit, just a little bit, of a function in the exponent place. So taking the log base 2 of both sides, we'll get rid of this 2 to the power of thing and liberate the exponent, which is x minus 3. Notice I've written that a little bit larger, and it is no longer in the superscript. Before we can do this, right, we need to make sure that our exponent is isolated. We'll see some problems where it's not in just a moment, but for now we have 2 to the power of something alone on the left-hand side of the equal sign, and so we can just proceed by taking the log base 2 of both sides. This is going to give me x minus 3 is equal to the log base 2 of 11. In order to fully solve for x, I need to move that 3 over to the other side as a plus 3. So this, log base 2 of 11 plus 3, would be my exact answer. This whole expression would be the exact answer. And this, 6.4594, is our approximate answer. Similarly, problem number 10 has some stuff for us to do. In fact, what we have to do at the beginning is isolate this e to the power of something. There's some other stuff over there to begin with. The way that isolating this exponent is going to look is by first getting rid of this addition by 4 on the left-hand side. Minusing by 4 on both sides, we now just have e to the power of something on the left-hand side. This is isolating the exponential. Now that the exponential is isolated, we can take the log, base e, or the natural log of both sides, and that's going to cancel the e to the power of and give us 4x, and accrue on the 7 to give us ln of 7. Now to get rid of times 4, we just divide by 4 on both sides to give us this exact answer, ln of 7 divided by 4. This is approximately equal to 0.4865. 11 is even easier because our exponential is already isolated. Taking the ln of both sides, we wind up with 3x is equal to ln of 13. Now we can divide away our 3, and that's our answer. Our precise or exact answer is ln of 13 divided by 3. Make sure that you're closing your parentheses here and dividing by 3 afterwards. And that means x is approximately equal to 0.8550. 12 is similar, but not exactly the same, because the exponential is not isolated first. There's a times 4 next to the exponential on the outside. So before I can proceed, I'm going to need to divide by 4 on both sides. Then take ln of that, which cancels on the left and accrues on the right, giving me the exact answer of ln of 15 over 4. Notice the parentheses now includes the 15 and the division by 4, and that's approximately equal to 1.3218 as such. 13 to 30 are logarithmic equations. We're going to solve them exactly, and we're going to need to check our answers after each one to make sure it satisfies the domain. Some of those aren't going to be so bad. We just need to keep in mind what is the opposite of log base 2 of something. Well, it's raising 2 to the power of something. And so what I like to do to show this work is to write a 2 underneath each side so that this left and right-hand side of the equation become the superscript of the 2. 2 to the power of log base 2 of something cancels and gives me an x. And on the other side, I get 2 to the 9. You'll also recognize this as simply going from logarithmic to exponential form. But essentially, we are just composing inverses with each other and canceling as such. 2 to the 9th is 512, and so that becomes our answer. 512 indeed satisfies the domain. Log base 2 of x has a domain of positive x's, and 512 is positive. This next one, we have to first isolate the logarithm before we're able to compose it with its inverse operation. So let's see what that looks like. That looks like doing this little bit of pre-work. First, we have to get rid of this plus negative 20 by adding positive 20 to each side. That cancels to 0, and it accrues on the right-hand side as a 14. Now we get rid of the timesing by 20 by dividing by 20 on both sides. That reduces to 7/10. Now we've isolated log base u. To proceed, we can just raise each side into the power of e. Composing e to the power of something with ln of that something will cancel, and we just get u. On the other side, we have e to the 7/10. And so that's what we want to type into the calculator. Now, that's going to be something weird, but not something that's too difficult to type in. My e to the power of button is right here, so we want second ln to get that. And then typing in 7/10 up here, we get our answer. E to the 7/10 is the exact form of the answer, while 2.0138 is the approximate form of the answer. You're going to want to include both forms of the answer unless it's something particularly nice, like it is for 15. For 15, we have log base 10, common log, of v is equal to 3. Just rewriting this in exponential form, or better yet, raising both sides into the power of 10, we get that v is equal to 10 to the power of 3. 10 to the power of 3 is 1,000. I should have mentioned a domain restriction in the last one. ln of u needs to have a positive value stuck in, but 2.01 is indeed positive. Same thing with this one. We have 1,000, and log base 10 of v has a domain of the positives. So we still haven't seen one that is going to give us any challenges as far as domain restrictions are concerned, but let's keep pushing forward. Number 6 has log base 2 composed with some function. However, since log base 2 is the outermost function here, and this other stuff is happening on the inside, we're going to be allowed to just immediately begin by raising 2 to the power of each side. This is because log base 2 is already isolated. If I do that, I wind up with 2 to the third on the right-hand side, which is 8. And I wind up with my argument, negative 6t plus 6, on the left. Now, we just solve this the usual way, minus 6 from both sides, and then divide by minus 6 to get rid of this coefficient of minus 6. This gives us t equals negative 1/3. Before I proceed, I should mention that we should have checked 16 for domain restriction. We require that this argument here be positive. That is to say, negative 6t plus 6 must be greater than 0. If I add 6t to both sides, and then divide by 6, I see that my domain is t's less than 1. And negative 3 satisfies that condition and is in fact less than 1, so we're good. We could also plug in a negative 1/3 inside here. This would give me a positive 2 for my minus 6t, and then adding 6 gives me an 8. Log base 2 of 8 is indeed 3 because 2 to the power of 3 is 8. So we could also check it by plugging in. But if your t or your variable as an answer satisfies the domain restrictions, it's going to work. 7 is an even easier one. We have only to raise both sides to the power of e to proceed. This gives us t equals e to the 10th. This is really even just a straightforward application of the change of form from logarithmic to exponential form. Your precise answer, your exact answer will be e to the 10, and your approximate answer is 22,026.4658 to 4 decimal places. Again, you can always see that change of form property as really composing both sides with an inverse operation. You're just doing the opposite operation on both sides, which is the same way that you usually solve equations. So what about 18? We might even begin with our domain restriction. That is to say, the only valid answers will be those for which 10z plus 3 is greater than 0. Solving, we get 10z is greater than negative 3, or z is greater than negative 3/10. So now when we solve this, we'll have to check that this is satisfied. To get rid of log base 10 of something, we raise 10 to the power of that something. Likewise on the right-hand side. That gives us 1/10 on the right and 10z plus 3 on the left. If I multiply by 10 to clear my fractions away, I get 100z plus 30 is equal to 1. Subtracting 30 to get negative 29, and dividing by 100, we get z is equal to negative 29 over 100. Now, negative 29 over 100 is just a little bit bigger than negative 3 over 10, which is negative 30 over 100. Because remember, negatives, the smaller the magnitude, the greater the number. And so this does satisfy the original equation. Observe that if we put in negative 29 over 100 here, and canceling our 10, we would wind up with negative 2.9 plus 3. But that is 1/10. And 10 to the power of minus 1 would give me 1/10. So we could also check our answer by plugging in here as well. Number 19 is going to give us our first example of an equation which does not have a solution inside of the domains. So also notice that it's the first time we have several logs on the left-hand side as opposed to just one. Let's see how those two are related. To begin with, we really want there to be just a single logarithm on the left-hand side. Now, there's other ways to proceed using properties of exponents, but let's just use our properties of logarithms. It will be equivalent either way. The main idea is that a sum of two logs is going to be the product of their arguments, with a single log being taken of that, right? Addition between goes to multiplication within. Now, we have just a single log base 4, and this can be canceled fully with 4 to the power of. So we take 4 to the power of each side, 4 to the power of 2 on the right-hand side, and we get 16. Now, if we bring over the negative 20t squared and the negative 36t that we get when we distribute this t into these parentheses, what we have is this polynomial equation, 0 equals 20t squared plus 36t plus 16. Notice each one of those is divisible by 4, so a nice way to proceed is to first get rid of that 4, factor it out, divide on both sides, but we got a 0 on this side, so the 4 goes away. Then what do we got? 5t squared plus 9t plus 4. That's the thing we want to factor. AC method, I drop a 5 in each place and a 1/5 out front. 5 times 4 is 20. Factors of 20 that sum to be 9 are 5 and 4, and so we slip those in here. Now all I have to do is reduce, and I get 0 is equal to t plus 1 times 5t plus 4. These have solutions at -1 and -4/5. However, take a look at the original equations. There was a log base 4 of t involved. This is only valid if t is positive. It does not allow negative t's or 0 t's. Therefore, -1 and -4/5 are neither of them valid solutions, and so there is no solution overall. These were our only options for solutions which would have made this true, and neither of them will work, because neither of them can actually be plugged into log base 4 of t. So, no solution. Number 20 is similar in that it starts out with a sum of logs. To deal with the sum between the logarithms, we take a single logarithm of the product of their arguments. That gives me x plus 7 times x plus 10 inside of a single log base 2. Once we have a single log, we can cancel it by taking 2 to the power of each side. On this side, then, we have 2 to the 2, which is 4. On the inside, we FOIL to get x squared plus 17 plus 70. Now I bring my 4 to the other side. That gives me x squared plus 17x plus 66. 66 has factors of 11 and 6, which sum to be 17, so it factors like that. And this gives me two answers, a negative 11 and a negative 6. Now, each one of these has its own domain restriction. One says it must be greater than negative 7, and the other says it must be greater than negative 10. Notice that one of these is stronger. If something is greater than negative 7, it's also greater than negative 10. But if something is greater than negative 10, it's not necessarily greater than negative 7, like, for example, negative 8. Now, that means we really should just be checking to see which of these is greater than negative 7. Negative 11 is not. In fact, it also fails this one too, but it only needs to fail one of them to fail altogether. Negative 6, on the other hand, is actually equal to this. If I plug in x is negative 6 in here, I get a 1. If I plug in x is negative 6 in here, I get a 4. A 1 in here would give me a 0, for my log base 1 of anything is 0. And a negative 6 in here would give me a 2, because 2 to the power of 2 would be equal to 4. And that is what we get. We get a 2. So yes, either by checking domain or by direct substitution, we can see that minus 6 is a solution. Plugging in negative 11 would give me a minus 4 in here, but that would be a problem. The reason this is happening is because we don't really have a way to distinguish between a negative times a negative being something, like 4, for example. Negative 2 times negative 2 could be equal to 4, but neither one of those would be valid once we separate the logarithms. Plugging in negative 11 here would give me negative 4, and that's not a valid argument of the logarithm. Or rather, I should say, it's something that's going to give us many complex values back, and we're really not at the right stage for dealing with that kind of thing. So we're going to have to throw out these answers. Long story short, you really just want to make sure you throw out that minus 11 and only keep the minus 6 as a valid solution. Let's look at number 21. Number 21 begins similarly in that we have a sum between logarithms, and so we write that as the logarithm of a product. Taking now 2 to the power of each side, we get, distributing our u, that minus 15u squared plus 16u is equal to 4. Bring these guys over to the other side, and let's factor. There's no common factor I can take out of each one, so let's plop a 15 in the first places and a 1/15th out front for balance. Proceeding with the AC method, 15 times 4 is 60, and going down a little bit on the list, we get a sum of the middle term, which was 16, from the factors of 10 and 6. Plug those in, and now reduce. I could divide a 5 out of this, giving me 3u minus 2, and I could divide a 3 out of this, giving me 5u minus 2. This means that 2/3 and 2/5 are my solutions. And notice that both of those are valid. Here we have that u must be greater than 0 because we're dealing with a log base 2 of u alone. Over here, we require that minus 15u plus 16 is greater than 0. And taking this 15 to the other side and then dividing it over, flipping my inequality, if you like, we wind up that u must be less than 16/15. But actually, both of these guys are going to fall into that region. Let's actually take a quick look at a Desmos graph and see what this looks like. So what I've done here is I've written out one side, the left-hand side of the equation, in red as the red curve. And on the other side, we have the constant value of 2, which is given by this blue curve here. Notice that our domains, which were that we had to be positive but less than 16/15, are indicated here. In fact, if I drop a vertical line at x equals 16/15, I can see that this is actually asymptotically approaching it from the left. Our two answers can be seen, number 1 as being less than 16/15, and number 2 as being these two values, 2/3 and 2/5. Remember, all of these equations can also be seen to have a graphical or a geometric interpretation. We are looking at, in fact, the intersection of two curves and wondering about how many points are valid intersections of those curves. If some polynomial madness had produced some solution in the negatives, that wouldn't have been valid because the domain of the function in red does not extend into the negatives, and neither does it extend over 16/15. The last three questions should be analyzed together in a certain sense to see that For equations that look like sums of logs equal to constants, we can either get two solutions, one solution, or no solutions. And in fact, there could be a richer structure to the number of solutions. It depends on what the arguments of the logarithms are. So from this, we see how important it is to check our domain and to be ready for there to be perhaps 2, perhaps 1, perhaps 0, perhaps something else, as a number of solutions to the equation. Problem 22 is somewhat similar, but now they have brought the logarithm over to the other side along with the constant. Let's see how that messes with things. The main idea is still that we want to isolate the logarithm, but now, rather than try to get this on the other side, what we're going to need to do is get the logarithms to be on one side and the not-so-logarithms, or just the numbers, to be on the other side. Once I've done that, I actually have a difference of logarithms. And the difference of two logarithms is the quotient of their arguments. So we can take a look at log base 7 of the quotient of x minus 2 and x minus 5. Now that we've isolated the logarithm, we can take 7 and raise each side into the power of 7. On the right-hand side, this gives me 49, 7 to the 2. On the left-hand side, we have composed something with its inverse, and so they cancel. This gives me just x minus 2 over x minus 5. Now, to deal with this rational expression, we first want to clear denominators. That means multiplying on both sides by x minus 5. Once I've done that, I really just have a linear equation to solve. And the usual thing that we have to check for a rational function, namely that we're not going to get a positive 5 here, is already something that we had to make sure of so that we wouldn't get a 0 of this logarithm. So that's kind of built in. But solving the linear equation looks like distributing the 49, then solving as we would any linear equation, group our x's together, group our non-x's together, divide by the coefficient, and we're good. It turns out that 243 divided by 48 does reduce by dividing by 3 into each one, and that gives us 81 over 16, or 5.0625. This number is indeed greater than 5, and that means it also, for free, satisfies that it's greater than 2. So we have a valid answer in 81 over 16. Number 23 has a combination of all of these things. We have a sum of logs and a difference of logs. Let's see if that messes things up too badly. We really just want to proceed the same way that we've been doing, which is to group things as a single logarithm with the properties of logarithms. That's one of the main uses of the properties of logarithms in this class, is to solve logarithmic equations with them by first grouping things together into a single log, and then composing that log with its inverse in order to cancel it. So log base 2, we compose into 2 to the power of. 2 to the power of 4 is going to give me 16, and foiling out this top part here, we're going to wind up with w squared plus 12w plus 11 over w plus 2. Now we want to proceed the same way that we would solve any rational equation, which is by clearing denominators and then regrouping the polynomial. Distributing my 16 here and bringing those terms to the other side, I wind up with w squared minus 4w minus 21 is equal to 0. A little bit of metagaming here. They're going to give you polynomials that factor. And so if you wind up not getting a polynomial that factors, maybe it's something like that, but also maybe go check your work and see if there's not something that you've done along the way, because, generally we want these things to factor and give us nice polynomial answers, integers or rationals, depending. Now, so factoring this guy, w squared minus 4w minus 21 is equal to 0, we get w minus 7 and w plus 3. They multiply to be negative 21, and they sum together to be negative 4. However, let's check our domain restrictions. Here, we needed this to be greater than negative 1, so that this argument stayed positive. Here, they had to be greater than negative 11, and here they had to be greater than negative 2. Of course, greater than negative 1 is something which will be stronger than both of these other conditions, because if something is greater than negative 1, then it automatically satisfies being greater than negative 11 or greater than negative 2. Unfortunately, negative 3 does not satisfy this, and so we're going to have to throw out that solution. 7, however, does satisfy each one of these. To make sure that our answer works, let's plug that into Desmos to check. Normally, I would say let's just plug 7 in, but 7 plus 11 is 18, and that's not really a nice power of 2. But maybe that's compensated for because over here we have 7 plus 2, or 9, which is also not a nice power of 2. So maybe these guys cancel somehow together. In fact, maybe you already see how that divided 18 divided by 9, that's going to give me a 2, and that is nice. But let's just double check with Desmos. How about that? Plugging these things in, right? Making sure that I, carefully copy the problem into the arguments here and setting a constant equal to 4, we find, yes, that is a perfectly valid solution, and -3 would be outside the domain of x's being greater than -1. So, right, even if something doesn't necessarily appear nice when we plug it in, that's not reason to fret. The division of these two, because this is a difference, bring that inside, that is going to be nice. 18 divided by 9 is going to be 2, and then that log base 2 of that will be 1, and so we have 3 plus 1, that's 4. So a couple ways that we could see that 7 is going to be a valid answer. All right, let's look at problem number 24. 24 is going to come along the same way. We use our property of addition here to bring multiplication inside, distribute that to get a polynomial, and raise both sides into the power of 2 to cancel on the left and give me a 4 on the right. Regrouping to set it equal to 0, factoring out our common term and canceling, and then factoring this as x minus 1 squared, we wind up with the solution of x is equal to 1. This is indeed satisfying the domain restrictions, which are that x must be greater than 0, and this one, in order to stay positive, bring that 8 over, divide by the -4, and flip the sign, and we see that we have to be less than 2. 1 is greater than 0 and less than 2, so this is going to satisfy. Now, all of the rest of these problems for this worksheet turned out to not have any answers. So let's proceed through these at a pace and see why it is that they mustn't have any answers. For number 25, we're going to have a rational to deal with. When we bring this inside of a single logarithm, the subtraction becomes a quotient. Now we also have a log base 5/2 of 4 on this side. All of these logs are going to disappear when we raise both sides into the exponent of 5/2. Now we just have to deal with this rational equation, clearing the denominator and then solving for z, we get z equals 0. However, checking our domain restrictions, we see that z has to be less than -8/7, and 0 doesn't cut the mustard. So there is no solution to this equation. 28 is similar. First, let's combine these logarithms together, which means multiplying a 3 inside, distributing gives me this. Now I can get rid of both sides by raising 3 to the power of each side to cancel the logarithms. Or, just set the arguments equal to each other. Logarithms are also one-to-one functions, so if the trick works for exponents, you might as well do it for logarithms too. Now that means that -24y minus 15 is equal to 9y minus 11, and now solving this in the usual way, we're going to wind up with -4 over 31, which is what I would say if 9 plus 24 was 31. Actually, it's 33. So our answer is going to be -4 over 33, but it really still doesn't matter. We require that this answer be simultaneously greater than 11/9 and less than -5/8. Hang on a second. Something can't be both greater than 11/9 and less than -5/8. Actually, this function here has an empty domain. If you try on Desmos to plot two functions, let's say log of x and log of minus x, we wind up with two fairly nice functions. Now, the one function in purple is defined for all the positives, and the function in black is defined for all the negatives. However, if I try to add these two functions together, I don't see anything. What happened? Is the graph broken? No, the graph has empty domain. There are no x's which simultaneously satisfy being negative for this one and positive for this one. No such numbers exist that are both negative and positive, and so no graph is appearing here when I try to add these two together. A similar but more complicated thing is happening if we were to try to graph this. The bottom line is that we never could solve this equation because there isn't really a way to have these two logarithms, log of -8y minus 5 and log of 9y minus 11, show up on the same graph with a common domain. So an interesting problem there, and one that we could have thrown out if we were careful at the very beginning. Let's check if something like that happens with 29 and 30. Yes, it does. Right here we have that we must be greater than 9. And over here I have that I must be less than -1. Things cannot be greater than 9 and less than -1 at the same time. And so we were never going to find any valid answers. We could try right? We could combine by addition as multiplication, we could get a polynomial, we could group it, we could factor it, we could get numbers, but none of these numbers are going to satisfy all of these. This is another one with an empty domain. Now, 30 is not exactly the same. It does not have an empty domain, but still it's going to have no solution. First, I would combine these things by properties of logs. Addition turns into multiplication, so I multiply each of these two terms by 6. On the other side, I have another log base 13, so setting these two arguments equal to each other, or if you like, raising each side into the power of 13, we cancel and get negative 24w plus 18 is equal to negative 9w minus 7. Grouping like terms and dividing away our coefficients, we wind up with 5/3. However, this does not satisfy this condition over here, and neither does it actually satisfy this condition over here. It satisfies neither condition, but it needs to just fail only one of them, and it is not, in fact, less than a negative. It's a positive number. So there's not going to be any solution to 30. Now, I know that this homework goes on to talk about some word problems, but I'm going to put that off into the next video. I think this video is already long enough, and I'm going to group all of those word problems together thematically. So if you'd like to proceed on to that video, you can get the answers to the problems that correspond to this section, that terminate this section. They will have to do with this, the compound interest formula, either for finite compounding or continuous compounding, which is one of the main places where E shows up as a continuously compounded model. So I'll let that be in the next video. Thank you very much for your patience. Have a great day and good luck with your studies. I'll see you in the next one.